You're watching a Channel 98 NBISD TV production.
Hey, welcome to Deja Vu. It's Algebra 2. As always, I'm your host, Kevin Corpy, leading you on a mathematical journey as always. Now today is kind of a landmark episode for us in terms of multiples of 10. We are on show number 20. That's show number 20 today. Kind of a bittersweet show though, because today unfortunately is also the last show that we're going to be looking at logs and exponents. So dry your eyes out there and pay very close attention, okay? Because you want to soak up all the logs and exponents today. We're going to be solving a bunch of log and exponential equations. Each of them are going to be kind of the same, but each one is going to require a slightly different method, all right? So take good notes. Download those worksheets and join me for about 30 minutes of Deja Vu. It's Algebra 2. All right, lesson 20, as planned, exponential and log equations, all right? First of all, let's look at exponential. I think they are probably the easier of the two. An exponential equation is basically this. It is an equation, first of all, so it has to have an equal sign. But it's an equation that contains one or more expressions that have a variable, and the important part, that variable has to be in the exponent. So it has to be the power. The variable has to be the exponent. Okay? We're going to look at a couple of ways to solve exponentials on today's show. Okay? If you go on to take pre-calculus, you'll learn a couple more advanced methods. But the easiest by far is what I call the getting the bases the same method, or that GTBTS for short. So here's what we're going to look for first and foremost. If I can get the bases on each side of an equation, in this case b is the base and b is the base on the other side. If b to the x power is equal to b to the y power, then because an exponential function is 1 to 1, that means that the exponents, in this case x and y, have to be equal. But that only works if I have a base to a power equaling the same base to another power. Okay? And of course, as always, for exponential and logs, the bases are going to be greater than 0, and they can't be 1. Now, you're going to see as we look at a couple of examples that that method is going to be a very isolated case and won't always work. So we have to have a more general method. And the more general method is to actually take the log of both sides. And that will work at getting the exponent out front onto the ground floor. We can solve for it because remember, logs and exponents are inverse operations of each other. Okay? So basically if I have a equaling b, then that means that log of a equals log of b, provided that a and b are greater than 0. Okay? They can't be 0 or negative. Now let's kind of put these into practice and you'll kind of get the feel for it. Let's look at this little example here. We have an exponential equation. It's 9 raised to the 8 minus x, so there's a variable in the exponent. We also happen to have a variable on the other side in the exponent, okay? But we only need at least one of them to have an exponential equation. Now notice in this case I have a base of 9 and a base of 27. Well, I can't write 27 as 9 to some convenient power, and I can't write 27 as 9 to some convenient power. So they're not direct integer powers of each other. But can I write each of them in terms of a common base? Well, with a little bit of practice and you're memorizing a couple of perfect cubes and squares, you could see that 9 is actually 3 squared and 27 is actually 3 to the third power. So they have a common base of 3. So I can ultimately get the bases the same. And here's what I'm going to do. I'm going to make a real simple substitution. I'm going to call 9 3 squared, because it is. Okay? And that's to the 8 minus x power. And over here, 27 is 3 cubed, and that's raised to the x minus third power. So I still have a power raised to the power. Here's where the rules of exponents come in. When you're raising a power to a power, you have to multiply these. And we have to be careful here because we're multiplying 2 times 8 minus x, which means I have to distribute. 2 times 8 is 16, minus 2 times x is 2x. So on the left side, I have 3 now to the 16 minus 2x power. On the right-hand side, I'll do the same. I have 3 to the 3 times x is 3x, 3 times negative 3 is negative 9. Now I have 3 to the something equaling 3 to the something else. That means the somethings must be equal because exponentials are 1 to 1. So essentially I turn the exponential equation into a little linear equation. And all I have to do is now solve for x. So I'll bring the 2x over here and bring the 9 across. 16 plus 9 is going to be 25. And then 3x plus 2x is 5x. And now I divide both sides by 5, and I get x is equal to 5. And we've got the answer. Okay? Now you can actually plug it in up here and see if you get the same answer. 9 to the 8 minus 5 is going to be 9 to the third power, which will be the same as 27 to the 5 minus third, or 27 squared. You can verify that at home. I'm going to show you another way to actually solve this on the calculator. All right, so there I am. Let's go ahead and show you how to do it on the calculator. We're looking for where the two equations are equal to each other. So if I go to y equals, I can put the first equation in y1 exactly as it is, put the second equation in y2 exactly as it is. Now I already went through and set my window to something where I could actually see where these two graphs share the same point, which is where they intersect. And so if I do that, I get this graph here. Now graphically, when I set two equations equal, I'm looking for, again, their point of intersection, which I can see is right there. You can find that on your calculator, remember, by hitting your second trace, which is your calculator option. Number 5 is the point of intersection, and it's going to ask you for two pieces of information. Is this the first curve? It should be blinking on one of the two, so when you click enter, it should automatically throw you onto the second curve. Go ahead and hit enter, and then scroll your cursor with these arrow pads to where you think it intersects, and then hit enter for your guess, and it'll scan, and notice it actually tells me, in this case, that it intersects at x equals 5, which is the solution we just found, and it also tells us a little bonus piece here. Remember, we plugged it into the left side and to the right side, 9 to the third and 27 to the second. That number is 729. The calculator gives it to us. So there's another way to find it on the graphing calculator. Okay, let's look at this example here. Now this one is also exponential. I've got a variable in the exponent, variable in the exponent. Now at first glance, I've got a 5 times something and a 40 times something. We're not going to be able to get the bases the same if I have these little constant multiples multiplied by my exponential bases. So getting the bases the same won't work. But if you look really carefully here, 40 is divisible by 5. So that might be a nice thing that we can do to at least get rid of it from one side. So if you divide both sides by 5, you get 1 over 32 to the 2x minus 1 equals 8 times 4 to the 4 minus 2x. Now again, your case might seem hopeless because you still have on this side 8 times a base, and you can't isolate it in terms of a single base. But wait! 1 over 32 is actually a hidden power of 2. 32 is 2 to the 5th. Helps to know that. 8 is a power of 2. It's 2 cubed. And 4 is a power of 2. It's 2 squared. So really, with a little bit of work, we can actually write all these in terms of base 2. So here's what we're going to have to do. 1 over 32 is the same thing as 32 to the negative first. Well, 32 is 2 to the 5th. So 1 over 32 is the same as 2 to the negative 5th. We can write it like that. Raised to the 2x minus first. And over here, 8 is 2 cubed times 4, which is 2 squared, to the 4 minus 2x powers. So what we can do now is we can do the algebra on the exponents. On this side, I get 2 raised to the distributing negative 10x plus 5. And on this side, I get 2 to the third times, now over here I'm going to have to raise a power to power, so that's 2 to the 8 minus 4x. I'm still not quite there, but I have 2 to the power times 2 to the power, and there's another rule of exponents saying that we can add those together. So I end up with 2 to the negative 10x plus 5 equaling 2 to the 8 plus 3, which is 11 minus 4x. And now with a little bit of hard work, a little bit of patience, and a little bit of insight, which you get by practicing a lot, you have 2 to the something equaling 2 to the something. So we can set them equal to each other. So I get negative 10x plus 5 equals 11 minus 4x. And now we're back in a little happy linear algebra equation. If I add 4 to both sides, I get negative 6x. Subtracting 5, I get 6. And then I divide both sides by negative 6, and you get x equals negative 1. And there, in fact, is the solution. You could plug it in and check and verify. Okay? So we were able to get the bases the same. All right, let's take a look at this one. I've got 4 to the x minus 1 equaling 5. Can I get the bases the same? 4 and 5 are not powers of each other, and unfortunately, nor are they powers of any common base. So I can't get the bases the same. So remember, our other method in this case was to take the log of both sides. That'll undo the exponentiation. So let's show that on a separate step. I get log now, and I'll use base 10. Any base will work. So I get log of 4 to the x minus 1 equaling log of 5. Now remember the rule for logs, it says I can bring exponents out front. So I get x minus 1 times log of 4, there's a parentheses, equals log of 5. Well, log of 4 and log of 5 now are just numbers that our calculator can handle pretty easily. So I'll divide both sides by log of 4. I get x minus 1 equals log of 5 divided by the number log 4. And then all I have to do to solve for x is add 1. So we get this final answer, x equals log of 5 divided by log of 4 plus 1 more to boot. And that right there is a simplified exact answer. You can plug that into your calculator, hitting your log button. Just be careful to close the parentheses after you punch in a 5 and a 4, and then add 1 to the end, and you will get this number. It's approximately, down here, 2.161. So I hope you're getting that. All right, so let's take a look at this one on the calculator as well. Once again, we have to go to y equals, and we have to type in the two sides of the equation, 1 into y1, 1 into y2. It doesn't really matter which one. Again, I've kind of set my window to something that's going to show the point of intersection. You can kind of play around with that on your calculator until you find where they intersect. But if you do, you should end up with a graph that looks something like this. I've got this horizontal line intersecting this exponential function. And again, I'm looking for where they intersect. So second trace, number 5. And if you only have 2 curves sketched, it should automatically put you on both of them. So hit enter for your first curve. It'll throw you to the other curve. Hit enter. And then go ahead and scroll to the point that you're interested in, which is actually more important when it intersects more than once. In this case, it does only intersect once, and there it is. It tells us that the x value is 2.160964, which is exactly what we found when we did it by hand. So in this case, it's a good verification. Let's look at this guy here. Slightly different. I've got 6 times base e. Well, e is irrational, and I got 5 times 2. So I don't think I'm going to be able to manipulate this to get the bases the same. So I already go to the method of taking the log of both sides. Now over here I took log base 10. Over here, since I have e, which is the natural base, I'm going to go ahead and take log base e of both sides, which is the natural log. So I have the natural log of 6e to the negative x equaling the natural log of 5 times 2 to the 2x. And now we have to carefully expand both sides using the property of log. Remember, the log of a product becomes the sum of the logs. So this is the natural log of 6 plus the natural log of e to the negative x. And on this side, I get the natural log of 5 plus the natural log of 2 to the 2x. And now, notice right here, the natural log of e to the negative x we've seen as a property. That's just negative x. So I get minus x equals the natural log of 5. And over here, I could bring the 2x exponent out in front. So that becomes 2x times the natural log of 2. So notice all those properties of logs that we did on a previous show, they are now the tools that we're using to actually solve equations, okay? They're not just a good for as an ends in and of themselves. We're using them as a means to solve something else. Well, now I'm going to underline my 2x terms. They're right there. And I'm going to collect them on one side. So I'll collect these on the left-hand side. So I get 2x natural log of 2 plus x, bringing him across, equals the natural log of 6 minus the natural log of 5. Now, I can't combine these like I did in Algebra 1 class. 2x plus 3x is 5x's, because the numbers 2 natural log of 2 are a little bit strange. But what I can do to magically isolate the x is to factor it out. So that leaves me 2 natural log of 2 plus 1 equals the natural log of 6 minus the natural log of 5. And I'm almost there. I'm rounding the corner. Now I have x times this number, so I have to divide both sides by that number. And my final answer here is the natural log of 6 over the natural log of 5, minus the natural log of 5, sorry, divided by 2, natural log of 2 plus 1. And believe it or not, that is a simplified exact answer. And when you plug that into your calculator, you'll get approximately 0.0764. So again, I took the log of both sides, expanded using the properties, exponents out front. I collected my x terms on one side, factored it out, and then I divided through by the number. That algebraic process right there is pretty typical. The only thing that's going to be different here is the numbers are going to be slightly different. But the process itself is pretty typical. So practice it a lot and you'll do fine. Okay, let's take a look at this one on the calculator as well. Now I'm going to show you a little bit different way to do this. Sometimes when you're graphing 2 separate equations and you're looking for the point of intersection, they may intersect at some y value that's not on the screen. So you have to look both left and right and high and low. You can take one of the variables out of the equation by doing this. Subtract everything from one side of the equation so that everything is now on one side and it's equal to 0. And now you're looking where that new equation intersects y equals 0, which is the x-axis. Well, you don't have to search high and low anymore because you know exactly where the x-axis is. It's the same thing as finding the x-intercept. So that's how I'm going to solve this one graphically. What I did is I subtracted the right side of the equation from both sides so that everything is now on the left-hand side, and I typed that into y1. You don't have to type in y equals 0, the right side of the equation, because that's the x-axis. So if I graph it, I get this graph right here, and I'm looking now for this x-intercept. Okay? Well, your calculator can find that by a different command. Remember, second trace now number 2. That's the 0 or the root or the x-intercept. And they'll ask you for a little bit different information. You always read the graph from left to right. So in this case, the left bound is going to be above. So as long as your cursor is above the x-axis, and mine is, I'll hit enter. And then you scroll to the right. If you don't have to scroll to the right to get to your right bound, you did your left bound incorrectly. So I'm going to scroll to the right until I can see visually and get a good confirmation numerically that I'm below. I'll hit enter, and then I'll hit enter for my guess, and it'll scan and find the x-intercept. And there it is. It's 0.7640363, which is exactly what we found again by hand. So your calculator is a very good backup resource when you're trying to learn skills. It gives you the confidence that you're doing the right thing. Oh, I don't know about you, but I need a quick break. All right, so let's take a quick public service announcement break. And while you're gone, think about this. What did the tie say to the hat? The answer when you get back.
Yesterday, my friends told me to smoke some pot, and I did. Then today, they said I should try and fit my fist into my mouth. It fits, but I can't get it out. I'm an idiot. I'm under the influence of others, and that ain't me. That's what he said.
Live above the influence. Above them, above weed.
Welcome back to Deja Vu with Algebra 2. I'm Kevin Corpy today, solving a bunch of log and exponential equations for you. Now, did you think about what the tie said to the hat while you were gone? Now, you did, huh? Didn't figure it out? Here's what he said. The tie told the hat to, you go on ahead. I'll just hang around. Yeah, the end of a bad joke means that it's time to get back to math. Okay. Just finished exponentials, had a couple of methods there. Now we're going to shift gears a little bit and go to log equations. Now log equations are, I wouldn't say more difficult, I would say more fun, more challenging. Okay, I like a challenge. But first thing about logs is they do have restricted domains. They have vertical asymptotes. We can't take the log of 0 or negative numbers. So we have to look at our final answers when we're solving them and make sure they work back in the original equation. The other thing is we have to actually condense and isolate logs before we can work with them. So here's how we're going to solve log equations. By the way, a log equation is nothing more than an equation that has a log expression that has a variable in it. Okay? So here's how we're going to solve log equations. First thing we want to do is isolate the log. Get the log all by itself. Now that may require a little bit of condensing using the properties of logs. Once I have it condensed and isolated, then I want to convert it to exponential using the conversion formula. And once we have it in terms of an exponential equation, now we can fall back on those other two methods for exponentials that we just learned about. So we can reduce it down to a process that we already know. We just got those two extra steps. Isolate and then condense. Isolate, which might involve condensing, and convert. Isolate and convert. Here's a nice little log equation. It's 2 log base 6 of 2x minus 1 equals negative 2. So notice my variable is inside the log. I'm taking the log of a variable expression. So I haven't really isolated the log yet because I have this 2 in front. It's like a coefficient of a log. And that's not considering isolating the log. So what I can do is I can divide both sides by 2. And I'll do that especially since negative 2 is divisible by 2. So if I divide both sides by 2, I get 2x minus 1 equals negative 2 divided by 2 is negative 1. Now look at there, I got log of something. That's isolated. So I will convert it now. So remember how to convert it. We go 6 raised to the negative first power equals the argument, the thing I'm taking the log of, which is 2x minus 1. Okay, now I'm back to a linear equation. Well, 6 to the negative first, that may be uncomfortable to work with. That's really 1 over 6. So I'll just go ahead and write that. And now I can solve it. I'll add 1 to both sides. So I get 1/6 plus 1, which is really 1/6 plus 6/6, or 7/6. And then I'll divide both sides by 2, and we end up with x equaling half of 7/6, which is 7/12. And that right there is the answer, 7/12, okay? So was that bad? It wasn't too bad at all. What did we do? We divided to isolate the log. We converted it to exponential. And once we converted to exponential, it wasn't even an exponential equation. It was linear. And then we solved it. We got 7/12, which if you're interested is approximately 0.5833. Okay, let's take a look at this guy. Another one. We got log base 12 plus log base 12. So I have two logs now, and they both contain a variable. So what I need to do then is I need to actually condense this to get it down to a single log. So they don't have any coefficients, which is good. And they're both base 12, which is also important. So I will pull log base 12 out. Now remember on the last show we talked about how to condense. Both of these are positive terms, so I'm going to multiply these two together. I get an x times an x plus 1. Okay? Now I've isolated the log, I can convert it. I get 12 to the first power equals this right here, which I'll save time and I'll expand. That's x squared plus x. What we have now is, again, not an exponential. We have a quadratic. So if I get everything on one side, since I have a squared term and a non-squared term, now I have a constant. I can solve the quadratic by the quadratic formula, or if we're lucky in this case, we can factor. Well, that would involve factors of -12 that add up to 1. And I think that's going to be x plus 4 and x minus 3. So it does factor nicely. And now, since I'm staring at the two linear factors, I know what the roots are. The roots are -4 and 3. Now, before you get in a hurry and you box those up and you maybe even put a little bow on it, suitable for shipping, okay, because you think you're done with all your solutions, remember we need to check these. We cannot take logs of negative numbers. And so everything that I find has to work in my final answer. Well, if I plug a -4 in right here, log of -4 is not going to work. Neither is log of -4 plus 1. So the -4 is an extraneous solution, we say. It came from the quadratic, which could have two solutions, but it's not a solution to the log. Let's try 3. Log of 3, that'll work. Log of 3 plus 1, that's a positive number. That'll also work. So 3 does, in fact, work. So of the two solutions that came out of the algebraic process, only one of them worked, and the other one was extraneous. We checked them for logs. Don't forget to check them. All right, now it's time for
Deja Review.
Yeah, Deja Review. Here we go. For the review today, what I'm going to do is I'm going to look at some log equations and exponential equations that are a little bit interesting. Maybe non-routine problems. Maybe you won't encounter these in your Algebra 2 class, but they are rather interesting. And understanding these types of problems will shed a little bit of light on how to do the problems that you may encounter. You're understanding the big picture, okay? So here we go. Let's take a look at this one here. We want to solve. That's a pretty simple instruction. Let's see if it's a simple operation. I've got log base 2 parentheses log base 3 of x equals -1. Now this is not multiplication. I repeat, it's not multiplication. That's not log base 2 times log base 3. This is what we call composition of functions. I have one log function inside of the other. In other words, I'm taking the log base 2 of another log function, and it's equal to -1. Ooh, how do we solve those? Well, let's work from the outside in. Let's pretend these parentheses are fortress walls that you can't see inside. All we see is we have log base 2 of something equals -1. Is the log isolated? Yes. So what do we do? Well, the rule tells us now if we've isolated the log, we convert it to exponential. So 2 raised to the -1st power will equal what's under my finger. Okay? Whatever it happens to be. Could be a log, could be an x, could be peaches. I don't know. Let's try it. 2 to the -1st equals, what was it? No big deal. It was that thing there. So that's what I'm at, converting it from the outside to exponential. Well, 2 to the -1st is 1/2, and I'm going to flip sides here. So really now I have log base 3 of x equals 1/2. Let's recalibrate. I've got a log right here. It's isolated. What do I do when I have a log and it's isolated? I convert it to exponential. So now I take base 3, raise it to the 1/2 power, which will be this, equals the thing I'm taking the log of, which is x. Well, that wasn't so bad. That is already explicitly solved for x. What is 3 to the 1/2? Well, another way to write that is the square root of 3. And the square root of 3 is approximately 1.732. So a little interesting example there. It's a composition of logs, not a product of logs. And if we just don't panic, we kind of work from the outside in, follow the rules, everything comes out to be pretty rosy in the end. All right? Now, here's the last example of the day. Look how interesting this one is. It's got a log and an exponential in it. Ooh! So how are we going to tackle that? Well, let's try the algebra. Remember that if it was a log, the rule says we convert it to exponential. This is isolated. So the base of natural log is base e. So I would convert that e raised to the this power, which will be e to the x minus 5, equals the x plus 5. So by doing that, I've unlogged the left-hand side, which means I've unlocked it, and I've got the x plus 5. And I could just subtract 5 and I'll have x equals. But, oh man, there's still an x on the other side. And notice by unlocking the log here by exponentiating both sides, I've basically trapped this x further up into an exponent. And there's not going to be really any way to get rid of that other than to unexponentiate it, by taking the log of both sides. So unlocking this locks that up. So that's not going to work. Well, what if I start with this side? I have e to the x minus 5. Remember, we could take the log of both sides. So if I take the log of e to the x minus 5, which is the right side, then I have to take the log of the other side. Well, that's going to be the log of x plus 5. Now notice what happens on this side. By design, I get x minus 5. So again, I have unlocked, essentially, the x from the exponent. But by doing that over here, I have now only put myself further behind the 8 ball in trying to unlock the x over here. I've actually buried it deeper inside of another log. So I run into the same problem. So algebraically, if you have a log and an exponential, each with a variable, it's going to be very algebraically frustrating, if not impossible, to unlock the x's. Okay? But there is a way. Okay, now that can be algebraically frustrating not getting an answer. So previously we've been using the calculator only to verify what we found by hand first. But in this case, the only way to solve it really is on the calculator, because algebraically the methods are too difficult. Okay, so let's go ahead and do that. I'm going to go ahead and graph them and find their point of intersection. So left side in y1, right side of the equation y2, and then hit graph. And one of them is logarithmic, which is this one here that's curving downward. And here's the exponential, and I'm looking again for where they intersect. So although we can't do it algebraically, your calculator is a number crunching machine, and it can actually find where these two equations actually intersect without having to do much math at all other than number crunching. It doesn't try to solve it algebraically. Second trace, number 5. First curve, it's got me on the log, I'll hit enter. Second curve, it's got me on the exponent, I'll hit enter. And then I will scroll to the right until it gets close to where I think it intersects. And that looks close enough. I'll hit enter. And it'll scan, it'll scan, it'll scan, and it'll tell me, there you go, boss. It'll say they intersect at x equals 5.8696059. And now we know. All right, 30 minutes. Up, so quick, so fast. We are out of time. Okay, I hope you learned something today. As always, you got to practice these things. Work a lot of problems. Don't limit yourself to the ones that I've worked on the show. Go to your textbook, and there's lots of problems in there. Just keep practicing. Ask your teacher for help if you need help. Email me if you have a question. I'll be happy to respond. Until then, though, until next time, Till then, criminy. 3, 2, 1. It's been one of those days. All right, 30 minutes come and gone so quickly. We are out of time, unfortunately. There's a lot of equations on today's show, and each of them is kind of the same but kind of different. The only way you're going to get good at them is to practice a lot of them. So don't limit yourself by any means to the ones I've done on the show. Go to your math textbook. There's lots of them in there. If you run out of those, ask your teacher or email me. I'll be happy to help you and give you some more, okay? Until next time, though, I am Kevin Corpy reminding you to do your homework.